Dimensionless form performance for the centrifugal forms. For a given pump, design the output variable H and the brake horsepower. Let me write. Output variable H brake horsepower bhp dependent on discharge of a function of discharge Q impeller diameter D shaft speed and at least other possible parameters are the liquid row density, viscosity, and the surface roughness epsilon. Does the performance curve of the pump, for example, this type of diagram, are equivalent to the following assumed functional relation. We have G, a function of Q, D, N as a discharge impeller diameter, shaft speed, density, viscosity, and the roughness. The second, BHP, also is a function of same parameters. Other dimensions are M, L, and T, and the other hence we have 7 parameters. So the number of dimensionless quantities, numbers, we have 4 dimensionless quantities with a with making a dimensionless exists a attachment theory. For example, pi theorem, we can obtain this relation as dimensionless number. The first one is epsilon on And the second one is the relation with the brake horsepower, bhp ON3D5 in these two relations. Let me write again the relations GH N2D2 Q on and D3 rho and D2 on mu. N is the shaft speed, note that, and epsilon on D. N is shaft speed, rotation, bhp on rho and 3d5, also the same. We know that the ND2 on mu is the Reynolds number, because this is rho and this is B. Epsilon on D is the friction roughness ratio. Three new parameters have arisen, which are: the first one is capacity coefficient, CQ, and D3. Head coefficient, CH, GH on N2, D2. And the last one is power coefficient, PHP Pro entry D5. Note that only the power coefficient contains flow density here. The parameters CQ and CH being kinematic type. Figure the performance give no warning of viscous or roughness effects. The Reynolds number are fully or fully turbulent. For all passage probability, the roughness is not given and varies greatly among the commercial pump, but at such Reynolds number are expect more or less the same percentage effect on all these pumps. Therefore, it is common to assume that Reynolds number and the roughness ratio have a constant effect, and the relations of the dimensions number of the pump, especially capacity coefficient, head coefficient, CQ, CH, and the power coefficients reduces approximately to this function. CH is a function of CP, and also CP is a function of CQ. For geometrically similar pump, we expect head and power coefficient to be nearly unique function of the capacity coefficient. We have to watch out that the pumps are geometrically similar or nearly to be called nearly so, because manufacturers put different size implemented in the same casing, thus violating geometric similarity. Large pumps have smaller ratio of roughness and clearance to the impelled diameter than the small pump. In addition to the more viscous liquid will have significant Reynolds number effects. For example, a factor of 3 or more viscosity increase causes a clearly visible effect on the CH and CP. The efficiency eta is already dimensionless and is uniquely related to the other three, and it varies with CQ also. Eta can be written as CH, CQ, and CP. Dimensionless suction head coefficient is also defined as CHS into D2, which is equals to the CHS is a function of CQ. The dimensionless non-dimensional data are then plotted in this picture. Eta, CH, CP, and CQ for the two diameters of pump, and also we have the specific shaft speed is not specific because it affects on CH and CP in the various data that should be read. Eta is a function of CQ, as here we have eta and other non-dimensional numbers. The coefficients Cp and Chs are seen to be correlate almost perfectly into a single function of Cq, while eta and Ch data deviate by a few percent. The last two parameters are more sensitive to slight discrepancies in model similarity, since the large bomb has smaller roughness and clearance ratio and a 40% larger Reynolds number. It defloats slightly more head and is more efficient. The overall effect is a resounding victory for dimensional analysis. The best efficiency point in the picture is approximately for CQ. For CQ we have the best performance, best efficiency, CP star eta maximum, here for example CH star and CHS. This value can be used to estimate BEP performance of any size bomb in this geometrically similar family. In like manner, the shot of head CH0 is equals and by extrapolation the shot of power can be obtained. And the maximum discharge for the shut off we have CQ max. However, this figure gives no reliable information about, say, the 28 and 35 impeller, which have a different impeller to casing size ratio and thus must be correlated separately. The next section is similarity rules and effect of viscosity.